Hello everyone, my name is Rich Ottinger and I am the Marketing Programs Manager for Park Systems, coming to you live from the Park Nanoscience Center on the campus of SUNY Polytechnic Institute in Albany, New York. Welcome to the 9th installment of Park Systems 2019 Material Science Research and AFM webinar series. Today's presentation is on the topic of surface plasmon resonance spectroscopy tandem with AFM. Unfortunately, again this month, our featured speaker, Dr. Rigoberto Advincula, is traveling and did not have confidence his internet connection would be stable enough to do the webinar live. So we pre-recorded today's presentation. In his absence, we will not have a Q&A at the end. That being said, you may still type in any questions you have into the questions module at any time during the webinar, and Dr. Advincula will respond in a follow-up email. With that all noted, please enjoy the presentation, and you can follow up with either of us with further questions if you don't get them loaded into GoToWebinar in time during the session. Enjoy the presentation. It is my pleasure to introduce to you Dr. Rigoberto Advincula. Dr. Advincula is a professor of macromolecular science and engineering at Case Western Reserve University and the editor-in-chief of MRS Communications. He is a fellow of the American Chemical Society and is the author of more than 250 peer-reviewed publications. Please welcome Dr. Rigoberto Advincula. Doctor.
Thank you very much, Richard, and thank you for our listening and viewing audience. I really appreciate the time that I can have with you and talk about surface plasmon resonance spectroscopy tandem with atomic force microscopy. Again, I'm introducing myself also for new viewers. I'm with Case Western Reserve University. I'm a professor at the Macromolecular Science Engineering Department. A nice clear day at Case, and you can see here the area view from a very cultural part of Ohio, where we have the Cleveland Museum of Art and the Cleveland Orchestra. So at the Macromolecular Science Engineering building, as shown here, my office is at the 5th floor. And we have a group that works on a variety of projects and problems from fundamental science to translational research and applied materials. And a number of things we do is very close to interfacial chemistry, in that we like to investigate nanostructuring, synthesis, different types of patterning modes, and basically interfacial phenomena, where we use the best tools, including atomic force microscopy and surface plasmon resonance spectroscopy, to probe phenomena and investigate new applications. So as Richard mentioned, I'm the editor-in-chief of MRS Communications. So I'd like to invite you to submit your best work and also proposals for review articles. So let's first talk about ultra-thin film multi-layers and assemblies. I like to use this view graph to introduce that nanostructured films, from polymer to inorganic to hybrid material, has many advantages in terms of nanostructuring when it comes to very, very thin films. I'm talking about film thicknesses from the 1 nanometer to hundreds of nanometer, and they can be ordered using chemical adsorption methods or by physical adsorption methods, where one can use Langmuir-Blodgett films, layer by layer deposition, surface initiated polymerization, or vapor deposition. Now, interestingly, surfaces and interfacial chemistry is also biological. In fact, at the air-water interface, which is one of the basic methods for investigating surfactant properties, one can look at the anisotropy of this phase, such that you can have selective orientation. Or one can look at micellar phenomena, formation of vesicles or higher ordered micelles in interfacial chemistry, and its importance in short and long range ordering. Now, of course, the best example is what can be found in living organisms, especially the bilayer membrane in cells and different types of proteins attached to it. The viscoelastic nature of that membrane is very important for the health of the cell and tissue integration. On the other hand, surface phenomena can also include sensors, DNA hybridization, and the investigation of tethering of macromolecules on a variety of surfaces. But today, I would like to focus actually on two techniques that can be combined, that can be a tandem, meaning one can be used after the other, and then see how they can synergistically provide information, whether one is dealing with the air and water interface or interfacial phenomena between liquids, or dielectric media as far as optical behavior is concerned at interfaces. So let me start by reviewing to you the theory of surface plasmon. So the best way to think of surface plasmon is the designation that it is a surface phenomena, an optical surface phenomena that is very sensitive to the dielectric medium and also the scattering vectors that are associated with that impinging light. Some people term it as surface light. In fact, the thing that you can relate very well is the localized surface plasmons found in gold. So if you look at gold, gold ring, gold earring, the gold shine or the gold color you observe even with colloidal gold is basically a surface plasmon phenomena. So in this case, we treat surface plasmon as a bound, non-radiative evanescent wave, meaning that the light intensity varies with distance from the surface. Its penetration depth into the dielectric medium depends on the wavelength of the incident light and the dielectric function of the materials. So you got different types of surface plasmon dispersions, basically depending on the dielectric material. And metal versus air or metal versus organic layer provides a very good contrast that makes SPR very useful for applications such as sensors or even photochemistry. Now, the other thing is, since it's a surface wave, it has characteristics that relate to amplitude, frequency, and so on. So what you see here basically in terms of the equation shows the relationship of that dispersion curve with the linear versus the nonlinear aspect. Now, I'll explain to you basically what is nonlinear. The nonlinear phenomena means that there's a light that is unaccounted for in a typical classical optics, where the unaccounted for light is actually accounted in terms of the light that propagates on the surface and decays over distance, time, or even frequency. So with this dielectric relationship, that means that a gold surface in a dielectric media with about 1.33 refractive index shows that this intensity varies with distance, and the direction of this decay is perpendicular to the interface, let's say specific with the wavelength of 850 nanometers. Now, the coupling of light to observe surface plasmon can be done several ways. One can basically have a prism, a light that goes through the prism at a particular angle, excites those surface plasmon on a metal surface and the dielectric media. Another is one can use a waveguide coupler. So you have a waveguiding layer, a substrate, and again, a dielectric media on top of the metal. So this surface plasmon mode, together actually with the waveguide mode, is used in a lot of sensing applications. And then finally, light can be excited using a grating. So this is a substitution for a prism, where again, depending on the impinging light or the angle, one can excite the surface plasmon. Essentially, the waveguiding and the surface plasmon is actually related to attenuated total reflection in many optical experiments. So again, here you can see some of the interpretations of an SPR APR experiment. So if you have light coming through glass and at the air interface without the metal, you have reflection. On the other hand, if you have a metal deposited on glass, you have total internal reflection up to a certain angle. And again, here you can see the three different modes by which that evanescent wave can be excited using a prism, a grating coupler, a waveguide, and particular optics. Now, what this translates, and this is really the more important aspect because of our limited time, is that surface plasmon can be utilized to investigate the dielectric properties of a thin film. So thin film, meaning you have a dielectric media of as little as 1 nanometer or less, or if you have a dielectric media in the order of microns, one can, of course, use wave guiding to investigate the properties. But assuming you have a thickness of about 100 nanometers, what will happen is as you excite the light using a what they call a Plasmon configuration, a type of ATR mode, as I showed earlier, where the light comes through a prism with a metal layer, that will result in a dip in the reflectivity curve. So as shown here, you have a prism and air surface. The reflectivity goes to a maximum at a particular angle and then becomes flat. That is the case of a prism without gold. But if you attach a gold surface on top of the prism made of glass, what will happen is as you reach the critical angle, it will start decreasing the reflectivity. Let's say in this case for silver metal, okay? So that dip is a very sensitive phenomena that relates to the dielectric medium. So this means that the light is actually being channeled on the surface of the gold film. Now, what happens if you put a polymer film on top of that gold is that this reflectivity curve shifts. As shown here in the dashed line, by adding a polymer layer, that curve or dip shifts to the right or at a higher angle. And in fact, this shift, if one can model them using different algorithms based on Fresnel algorithms, one can actually calculate the thickness and or the dielectric medium. The other aspect is this type of experiments are very sensitive to polarization, such that an S or a P mode can be distinguished based on the type of polarization experiment one does. Now, the other thing is the graph below shows that as you have this shift or dip in the reflectivity curve, one can also monitor the scattered light or the intensity of the scattered light by putting a detector in front of the surface. So this scattered light actually in many instances is very useful as well for development of sensing or investigating phenomena. Now, as a way of modeling, one can change the thickness of the film. Let's say the dielectric medium shifts from 10 to 100 nanometer. You can see almost a linear shift on the reflectivity curve towards higher angles as you have thicker films. Or if you have a dielectric constant change as a function of the real part of the dielectric constant, or sometimes we call refractive index. That means if you change that value from 1.5 to 2.7, that value also shifts. So this is one rule which you can say with the SPR curve is that you either have to fix the thickness or fix the dielectric media, but if you start changing both, then it's hard to model or account for the influence of one over the other. Another is that absorption changes, which is more of the imaginary part of the refractive index. Let's say if you change the absorption from 0 to 0.5, you see here that the dip in the curve changes as well. And as you increase the imaginary part of the refractive index, the dip becomes shallower. So that means we can actually do some modeling or simulate the SPR curves. Now, schematically, the experimental configuration of an SPR experiment is that you have the incident laser on top of a prism, a gold that was coated or attached to the prism using a dielectric media layer, and then you have your organic film or the film that you want to sense. This sits, let's say, on top of a goniometer, a theta axis goniometer, for example. On the other side, you have the photodiode detector. So the light coming to the prism means that it's interacting with the metal and the dielectric layer. That in turn, depending on the angle as well, is detected as a change in intensity or reflectivity by the photodiode. Now, to integrate the whole thing in terms of sequence and waves, one has to use a lock-in amplifier, a chopper, and all the best optics to get clean waves. And then, of course, readout could be on, and control could be on the computer interface. So for short, this experiment allows us to look at the decay of that evanescent field with regards to distance from the surface, or with regards to changes in reflectivity as a function of time. So schematically, what is shown here is that over distance, the evanescent wave decays as you go farther and farther away from the prism. So this coupling means that it is sensitive to thickness changes or dielectric changes as well, as mentioned earlier. Another thing is this open configuration as shown here allows us to do hyphenated techniques, which allows us to do a combination of AFM, QCM, put the whole environment so we can control the temperature, do electrochemistry, and even a controlled pressure chamber. Now, as you can see here, various experimental configurations of the SPR. The two ones on the side are actually set up that we have in our lab, as well as the middle one. But you can have commercial setup that is optimized for flow conditions, as well as sensors that have a small footprint. Now, how can we use this otherwise as a sensor? One of the things that you can rely on is the shift that occurs as you add a dielectric medium on top of gold. And this shift, as reduced here, shifts to higher angles. Now, if you observe the intensity at a fixed angle, you can draw this red line. That means that the intensity or reflectivity is different from the original gold surface all the way to the added organic film. And that means as you are increasing the thickness or the dielectric shift on that organic film sitting on top of gold, and then you simply monitor that as a function of time, let's say in a flow cell condition, that actually becomes a kinetic experiment. In other words, one can observe reactions, binding assays, specific or non-specific adsorption, chemisorption, physisorption. So it is actually making it a very useful tool for kinetics experiments, okay? And various configurations or hyphenated techniques, as I mentioned earlier. One can combine SPR with a high pressure temperature cell setup. One can look at the light scattering microscopy together with SPR, or one can couple the SPR probe with the microscope, so you can have what we call SPR imaging, or you can set it up so that you have flow cell delivery with various types of fluids where you can monitor the kinetics of adsorption of a molecule or a polymer on a surface, or monitor actually electrochemistry. Now, more of the electrochemistry, we have played for many years a unique setup where you can actually do electrochemistry on the surface of a gold working electrode, which actually doubles as a coupling surface, a dielectric coupling surface for an SPR experiment. So in fact, this is already a hyphenated technique where we can observe changes on the dielectric medium on top of gold, the working electrode, where we combine it with an electrochemistry experiment, such as dynamic cyclic voltammetry or static potentiostatic deposition, or sometimes even doing experiments including impedance analysis. That means that the whole thing will allow us to measure the thickness changes of an electrochemistry or electrodeposition experiment, or will allow us to monitor the electropolymerization or even the redox kinetics, reduction oxidation kinetics of a dielectric layer that is electrochemically active on gold. So this is already a hyphenated technique that we have reported in many cases. Now, other than this, you can actually do many things. You can monitor scattered light using a photomultiplier. You can actually combine it with fluorescence. And my last point is you can actually combine it with atomic force microscopy, which we have demonstrated a few years ago. And I'm going to explain that further. Now, in summary, what you have is the ability to create experiments probing surfaces, multi-layer film deposition, electrochemistry, combine it with microscopy and spectroscopy, and then ultimate applications for environmental monitoring, sensing devices, monitoring corrosion, biological events, okay? So there's a lot to be gained in terms of knowing this technique and how it can be applied to surfaces. Now, I would then like to combine it with atomic force microscopy. But before I do that, of course, I'd like to review AFM for those who are listening for the first time. AFM essentially is a surface probe microscopy technique that allows you to probe surface forces or even properties based on the dielectric, electrical, magnetic properties of a particular environment using that probe tip and substrate interaction. The important thing, and this has been the main use of AFM, of course, is imaging. That is, one can investigate morphology based on surface properties, and eventually experiment with the deflection properties of that cantilever with regards to a laser light impinging on the tip and a photodiode array. So it is best explained by this diagram showing that AFM is essentially a rastering technique with a piezoelectric element so that you can have an XY movement while you're trying to maintain that voltage or that surface force, and there are many ways to configure this experiment. Ultimately, the image or the digital image is derived from the deflection of this cantilever tip with the impinging laser light as detected by a position-sensitive photodetector as shown here. Now, the variety of designs from the piezoelectric scanner coupled or decoupled with this sample or cantilever, and of course, much can be said about the interaction of a tip, a sharp tip or not so sharp tip with the surface, eventually boils down to the type of design or scanner design that one deals with. So outlined here are three possible designs where you have the piezoelectric element as part of the sample or part of the cantilever tip, or a technique where you have the XYZ piezo tube scanner independent from the sample. And each of these configuration can have advantages or disadvantages, open or closed system. But uniquely with Park systems, you have a unique design that has a separate Z scanner, XY scanner, which effectively decouples the XY sample substrate over the Z direction. The result is you have a very sensitive scanner, accurate, especially on the Z direction, so you can investigate trenches, There's no bowing effect. You have very high resolution. You tend to keep your tip for a long time, less sample damage, and of course, in many cases, very easy to use. And as a disclaimer, we have actually a Park AFM system and extend that we use. But otherwise, this summarizes the things you can do on an AFM. You can actually modify the tip so it can be sensitive to the surface by organic media or different types of functionalization, including particles at the cantilever tip. The substrate itself can be mica, gold, or silicon wafer. It can be fairly flat, very flat, and quite forgiving. As mentioned, if you couple the force curve measurements, the compositional mapping, one can probe the surface forces, the friction, the non-contact mode, the electrical force, addition force, etc. Again, time will fail me to give this unique applications in the biological event, which is necessarily done in a liquid in situ environment. This can be used to probe protein-protein interactions, antigen-antibody, DNA hybridization, and so on. So again, we have a Park and Extend, very useful for a lot of experiments. We can distinguish topography, phase imaging, and hybridize the technique and actually do conducting AFM, dielectric AFM, electrostatic AFM, and so on. So I'll leave that for you to examine the other webinars very specific for introducing Park AFM system. So with the last half of our webinar, I actually like to focus on the projects we have, where we have combined surface plasmon resonance and atomic force microscopy in several projects. So let me start with a work that we've done almost 18 years ago, where we actually reported many systems involving electropolymerizable polymer precursors that deposit as cross-link systems on a gold substrate surface or working electrode, and we can have essentially a conducting polymer with all its redox behavior and deposition modes. So one of the first papers we published was the electrodeposition of polythiophene. The polythiophene we deposited was uniquely synthesized in that it's actually tethered to a polymer. And polythiophene, of course, can be polymerized with a variety of metal-mediated reactions or oxidative methods. But here, we electropolymerize it using a cyclic voltammetry setup. In this case, the first use was to investigate the deposition of the films with a variety of thicknesses increasing with each deposition cycles. So as you can see here, as we increase up to 12 cycles, we actually measure the thickness all the way to 75 nanometers. And at 3 cycles, you can easily see here the shift in the Plasmon curve to higher angles, indicating the increase in thickness. Again, using a device like this. So what's important here is SPR was used to monitor the thickness shift per deposition of several cycles of the polythiophene. Now, ex-situ wise, we then investigated by AFM the morphology, both on the topological and phase imaging, the domain behavior as we increase the number of layers deposited. So AFM here was used ex-situ, meaning after we have deposited the film. So in this case, we can see that the domain sizes increases as we have more films deposited. We actually have some AFM imaging that distinguish a reduced versus an oxidized state. So this is a very good combination of the two techniques. Now, a lot of things we developed later on involve what we call in situ measurements that combine electrochemistry and SPR. As shown here, we have the electrochemical parameters on the deposition of what I call a precursor polythiophene derived from this terthiophene oligomer that we attach to a polymethyl methacrylate backbone. And what happens is that as we deposit them by cyclic voltammetry up to, let's say, the 4th cycle here as shown, the amount of charge can be calculated based on the electrochemistry experiment with the various copolymers and compositions with carbazole. But what's interesting is that with reflectivity, we can see the change in the intensity or reflected intensity per cycle. So what you can see here is we go to a phase of oxidation, reduction, oxidation, reduction. In the meantime, as you increase the cycles, you actually increase the reflectivity, which actually when measured under a fixed angle indicates a shift in the Plasmon curve. Now, depending on the voltage, which is a picture of the redox behavior, here are the raw reflectivity curves as a function of incident angle. So what I can summarize here is different types of polymer and their various oxidized states going to 1 volt tends to shift the thickness and the dielectric media or the dielectric property of the deposited film with various thicknesses and copolymers. So in this case, SPR and electrochemistry was investigated or done in situ or real time. Now let me shift to another example. We have here an electrochemical SPR configuration. We then deposited a film, a patterned film on a surface in situ and then ex situ. And then finally, we eventually have a polymerized polypyrrole on that pattern as shown here. So electrochemistry allowed us to investigate the redox behavior. In situ wise, the deposition of the polymer produces a shift to higher angles of that reflectivity curve. But again, AFM is a very important tool for us to combine with. Here is actually the AFM micrograph of the patterned deposited film based on self-assembled monolayer pattern surfaces where the polypyrrole selectively deposited on the dots. And here are optical micrographs showing the changes in intensity with deposition, as well as the changes in intensity here as you go in and out of the Plasmon curve of the deposited film. So for clarification, this experiment actually is an SPR imaging setup. So the images you see here are actually optical images as one goes in and out of the dip on the curve, indicating the changes in the dielectric media as a function or investigated with a specific shift in angle. Now, let me go this time to how we have combined electrochemistry, SPR, and AFM. So actually, this is a 3-in-1, 3 instruments in one, in that we were able to monitor the electropolymerization of PDOT simultaneously while doing SPR, electrochemistry, and AFM. So this was possible because we use an open AFM system where we actually located it at the center of a theta-theta goniometer. So rotating these arms using a theta-theta goniometer means that we can do an SPR experiment. So here we have the laser detector, we have the prism, we have the gold surface. In fact, the third component here is the gold surface, as shown here, is actually a working electrode in an electrochemical cell. Now, this electrochemical cell actually is sitting below this AFM. So we can have a cantilever tip that is close to the gold surface. And as we deposit the polymer, all 3 can be run simultaneously. So in this case, we can have an in situ, real-time deposition of the polythiophene monitored by AFM, electrochemical method, and SPR all at once. So the result is this. We actually have 3 graphs that can be plotted as a function of time. So we can monitor the potential. So as we oxidize, reduce, we can then do the AFM imaging in one line. So it's very important to say that this was done in one line to preserve the time frequency. You can see here the shift in morphology as you go from 0 to 1.2 volts. So that shift in the morphology is actually quite interesting in that it exactly relates to when you shift from an oxidized to a reduced mode or a negative potential. And then here you can see where you actually stop the voltage injection or the electrochemistry setup, and then again you observe the morphology on one line. So this is not a spatial AFM, but this is a temporal AFM. At the same time, you can monitor the charge injected from the electrochemistry setup. And then more interestingly, you can do the reflectivity measurement as the film is deposited. So this dip in the reflectivity and the fact that we can measure the SPR indicates that we actually deposited a film that resulted in a dip in the curve, SPR curve, because of that added dielectric material. Now, if you plot this as a function of potential, one can look at the AFM roughness changing with different cycles. You can see the shift from oxidation to reduction, and then finally the change in the thickness / dielectric as a function of deposition of the film from oxidation to reduction. Okay, so this is what I call a real-time in-situ monitoring 3-in-1 experiment with electropolymerization of PDOT. Otherwise, we can have the SPR observed using a typical ex-situ SPR experiment, which shows the dip in the curve. But then we can take the same film and then do a normal AFM imaging. So here you have the gold substrate before deposition, and then here after the film has been deposited on the surface. Okay, so this is basically a normal AFM imaging experiment. And just to give you another window, this one, we have a potentiostatic deposition. So what we did is we ramp up the potential to about 0.8 volt, 0.9 volt, and then we stabilize it further. We did the AFM single line or single point rastering, showing again the change in morphology as you shift to a higher potential. Not as big as the cyclic voltammetry experiment, but nevertheless discernible. And then this charge as we inject the electrons in a constant potential. And then of course the change in the dielectric media that was monitored using SPR. So in summary, we monitored the electrodeposition of PDOT using both cyclic voltammetry and potentiostatic method, investigating the real-time phenomena and ex-situ investigation with a combined electrochemistry, SPR, and AFM experiment. Now, let me then shift to the last part of my talk, which is sensor design. And sensor means that we can have the surface plasmon resonance as a sensor for a sensing element that's deposited on the gold substrate surface. And then we can couple that with various chemistries or layer film configurations that make it sensitive. For example, we've actually reported 2 systems for glucose monitoring where we combine the glucose oxidase with the conducting polymer. We prepared it by layer or electrodeposition methods. Actually, this reference here refers to another paper. But what we have is this sensitive layer or dielectric nanostructured layer on top of a gold surface that serves as the SPR coupling for or production of that evanescent wave. So if you do that, one can monitor the deposition of the film. One can also monitor the redox cycle. One can monitor the change in potential or current simultaneously with the reflectivity changes. So as you can see here, by conducting an electrochemistry SPR deposition on that sensing layer, we can have both data, reflectivity and current, as a function of time, which is very useful for monitoring both the deposition and redox properties of the sensing element. Or we can monitor in another experiment the sensing of glucose before and after, which is actually shown here, a raw curve that demonstrates the shift in the Plasmon curve with the detection of your glucose. And more information can be gleaned from this paper, which I'll just refer to here and encourage you to look up the original paper. Now, another experiment we did is in a series of sensors using molecular imprinting. In fact, one of the papers we reported based on a dendrimer that was electropolymerized on an SPR electrochemistry setup was for the detection of a nerve warfare agent or analog, because I don't want the real thing in my lab or close to my students. So we use this model to essentially polymerize a dendrimer on top of a gold substrate surface. This dendrimer has ions, copper ions, that can complex with a analyte such as this sarin and soman analogs or methylphosphonic acid. The bottom line is this is an SPR experiment with an electrochemistry setup for deposition of the dendrimer film, and then we use this for sensing. So as a sensor, one can monitor the response based on reflectivity or potential. Okay, that means that as we introduce increasing concentrations of the PMP analog or sarin analog, we can see an increase in reflectivity, indicating a linearity of detection. On the other hand, this was also confirmed by potentiometry. But what's interesting is this detection goes all the way to nanomolar limits. In fact, just to demonstrate what we call selectivity, this sensor was sensitive for PMP, EMP, but when we introduced DEP, acetic acid, sodium phosphate, the response was low. And we attributed this to the very good complexation behavior of this PMP and EMP against the dendrimers. And then finally, the nanomolar sensitivity was extended to what we call picomolar sensitivity by looking at the reflectivity change as well with a final breakdown MPA acid. So to summarize, what I've shown here is you can do SPR sensing towards a nerve agent. Now, more chemistry in that we actually tried to mimic the behavior of an enzyme on a substrate through what we call molecular imprinting. What we have here is a design to take a chemical agent or analyte, complex monomers around it, polymerize or cross-link this complex, and then finally you'll end up with a cavity that is the exact fit of the template. So this interaction is a lock and key mechanism and actually is very close to what you would call an enzyme. So this is a artificial enzyme or plastic enzyme. Moreover, this artificial enzyme was actually attached again to a surface plasmon resonance surface. So using the surface as a working electrode to electropolymerize the deposition of this complex, we actually use electrochemistry to get a very controlled dielectric film, we then use SPR to monitor the binding kinetics or assay of the original analyte or competitive analyte on the surface. So in other words, we created our own sensing element using the MIP approach. So one of the first papers we published was actually the detection of caffeine, theobromine, theophylline. Again, using this concept where we electrodeposit the complex of the monomer and the analyte, we deposited it on the gold side of the SPR, and then finally we did the chemistry. One thing is that we were very particular in this paper to design the right monomers. And again, you can look at the original paper to look at how we have synthesized and designed this monomer so that we can have a very good complex and electropolymerize them by cyclic voltammetry. Now, we actually do a lot of modeling to optimize the system. So here you can see an ab initio calculation where we complex the analyte, in this case theophylline, with two monomers of the G03T electropolymerizable monomer, and then use this complex to deposit on the film. So I'll just go fast forward to the results. The result is you have a very sensitive sensor with naproxen as a template, or theophylline as a template, or paracetamol as a template, with very little response from the other molecules. Another is we can calculate the linear sensitivity, the limit of detection. These are very stable sensors with up to about 1 to 2% retention, and even at 45 days it still works. So in other words, in a series of papers, or actually another webinar, we demonstrated that these sensors are unique, and you can use SPR as a method. Now, finally, and this last example, we actually use quartz crystal microbalance to sense folic acid using this molecular imprinting technique. And to summarize it, and I want to close using an AFM image, we then image the topography of the imprinted and the non-imprinted polymer, or sometimes we would look at before and after sensing, and then we would use AFM to investigate the changes in morphology as the analyte binds to the surface, specifically or non-specifically. And again, referring to the original paper, we discussed further the importance of AFM combined with SPR to get a complete picture of the phenomena or an optimized sensor. So with that, I don't have any conclusion slides, and you feel free to email me if you have any questions, or during the webinar, please ask Richard for some of those questions, and it will reach me. So with that, I'd like to thank you, and I'll be happy to answer and connect with you.
All right. Thank you, Dr. Advincula. And I want to say thank you to everyone for joining today's webinar. Once again, we cannot take live questions this month, but I'll be able to ask my usual final question, which is, can you give us a brief preview of next month's webinar topic, nanotechnology in plastics and packaging?
Thank you, Richard. Again, please feel free to reach Richard or email me some of your questions with today's topic. So next month, we will be focusing on the application of nanomaterials in packaging. Basically explore the advantages of using certain nanomaterials, or the phenomena that we can investigate or take advantage of in terms of barrier properties, antimicrobial properties, non-wetting properties, etc., in a lot of packaging and even coatings applications. So something different, but again, I will emphasize that atomic force microscopy is one of your best tools to characterize surface phenomena, nanostructuring, and the use of nanomaterials for such applications. So with that, I'd like to thank you, and wherever you are, good afternoon, good evening, good morning. Hope to see you again.
Thank you, Doctor. And as Dr. mentioned, you can continue to put your questions into the questions module as I wrap up the webinar here, and we will collect those and get answers back out to everyone. Please join us for the next session on Wednesday, October 16th, once again at noon Eastern Daylight Time. And thank you all for joining us for this session of the Park Systems 2019 Material Science Research and AFM webinar series. If you have been enjoying this webinar series, we hope you will consider joining us for the 2019 Nanoscientific Symposium on SPM, held November 19th and 20th here at the Park Nanoscience Center at SUNY Polytechnic Institute in Albany, New York. The symposium is a venue for researchers, scientists, and engineers to learn about the latest studies being formed using SPM, featuring speakers including Dr. Advincula and many other industry and academic experts. Visit live.parksystems.com for registration information. Thank you once again for joining, and you can find more information about Park Systems AFM at parksystems.com. Please direct any AFM questions you have to inquiry@parksystems.com. If you have any questions specific to this webinar series, or think of questions for this edition of the webinar that you'd like me to pose to Dr. Advincula, feel free to reach out to me directly at richard@parksystems.com. Thanks again, and we'll see you next month.